Hello, welcome you all. Hope you are doing well. Today I will discuss the topic from physics, which is gravitational potential energy. This topic belongs to physics of class 11th under chapter gravitation. So let's see how we'll proceed the class. First, I will define the gravitational potential energy. Then there will be a derivation to calculate the value of gravitational potential energy at any point. After this, we will practice some questions to get some clear picture of these two. Okay. The derivation will be on the basis of definition. So understanding definition is more important. Okay. After completing the class, you will be able to define or you will be able to calculate potential energy of a small object of a point mass m placed at a distance r1 from a spherical object. Okay. So after this video, you will be able to compute the gravitational potential energy of this mass at this position. Okay. So now we have a clear picture and a ready target. Okay. Now let's proceed with the definition first. So yeah, before discussing this, let's see the term potential energy. So this is a well-known term, which is nothing but a tendency to do work. Energy possessed by object which can do some work. Okay. But there is an additional term, gravitational. This is gravitational potential energy. Potential energy of so many kind. Like when you extend spring or rubber, the potential energy gets stored in it. When you squeeze a elastic ball, potential energy gets stored in it. All those was due to changing in shape. Those are under elastic potential energy. We are not going to cover in this lecture. Okay. So what is gravitational potential energy then? Gravitational potential energy is due to gravitational field of another object. Okay. So let's see. This object, let's say this is Earth and having mass me. Okay. Earth have some gravitational field, and if you place a mass, point mass m at this point P, then it will have some potential energy due to gravitational field of this. Okay. If you place this mass at this place, it will have some different potential energy. We are not going to change shape of the object. It's due to position. We are just positioning it. Now it's at point P. It might be at another point Q. Let's visualize it. Suppose, yeah, I am on Earth and there is a gravitational field. So this object have some gravitational potential energy. This object have a mass small m, Earth have a mass capital M or me. That's why this object have some gravitational potential energy, because it is placed in a gravitational field of Earth. How you can verify it has some gravitational potential energy or not? See, at this place, kinetic energy of this object is zero because it does not have any velocity. When you release it, see, you heard a sound. From where this sound energy come? Was there any kind of explosion? No. That sound energy come from the transformation of energy. See, there was a potential energy. It get transformed into kinetic energy. And that kinetic energy is lost now. At this position, this has zero velocity. It does not have any kind of kinetic energy. From where those kinetic energy gone? Some disappear in form of heat energy, what you have here. And there might be some molecular deformation at molecular level also. So you have seen there is a gravitational potential energy on this object, of this object. Now let's define it. Potential energy of any object having mass m is defined as work done by external agent. Work done on this object by external agent in bringing it from infinity to that point. That work done is equal to gravitational potential energy at that point. And there are some terms condition also, like this object is moving slowly. You are bringing this object from infinity to this point slowly without changing any kind of kinetic energy. And this condition is very important. Okay, so the definition is gravitational potential energy of object is defined as work done by external force. Work done by external force. I am showing the external force F-E-X-T, this W for work done. Work done by external force on the object in bringing it from infinity to any point P. Let's say this point have a position R1 with respect to center of Earth. Slowly or without gaining any kind of kinetic energy. That means change in kinetic energy is zero. This is definition. Gravitational potential energy is defined as work done by external force in bringing it from infinity to that point slowly without changing kinetic energy. Fine. Now let's have a clear picture of this. Suppose this object, I have to calculate gravitational potential energy of this object. So according to definition, this object is an external force is applied. Who is applying external force? Me. I am applying external force on this object to bring it from infinity to this position and moving it slowly without changing kinetic energy. Okay. Now let's see. Suppose this distance, at this distance r is tending to infinity. See, this is very large distance. Okay. From there, I am moving this mass. Yeah. At starting, the mass was there. After it was there, then it was there. I am moving mass slowly. Okay. There is a term work done by external force. Now let's see how external force is acting on it and how to calculate work done. See. Suppose starting point is this and I am moving along this line. Yeah. After some time, at any instant, this mass was there. At this place, the acceleration of this object is 0. The mass is moving slowly. Now visualize by drawing free body diagram that how many forces are acting on it. One force is gravitational force acting downward. And you know the magnitude G, mass of earth, mass of object by r square. What will be the distance between them? And another force to balance it is acting in opposite direction, that is external force. External force must be equal to gravitational force in magnitude and acts in opposite in direction just to balance it. If you balance, then the net acceleration of this object is 0 according to Newton's third law. Net force acting on it is 0, then acceleration will be 0. If acceleration is 0, then velocity changes will be 0, and if velocity changes will be, that means change of kinetic energy is 0. This was condition fulfilling it. Okay. So force. Now work done by external force. You have studied that work done by a constant force is force into displacement. That was it. And work done by now we have to see if this force is constant or not. At this point, a gravitational force was acting on it in downward direction. To balance it, we apply a force in opposite direction. Let's show it this position. Applied a force, external force, and a gravitational force was acting on. And after some time, this object is at this position. Here gravitational force is acting on it, and to balance it, another external force is acting on it. External force at this place and external force at this place is not equal. Let's see. Force, gravitational force acting on it is G, mass of earth, mass of object by r square. This is constant, mass of earth is constant, mass of object is constant, only variable is r, which is in denominator. At this place, at this position, the object is as the r is more. At this position, the distance from the center r is less. See, If this is more, the value of this will be less, and if this is less, the value of this is more. That means gravitational force is increasing as the object is proceeding towards Earth. Okay, and to balance this, at this place external force is equal to gravitational force. At this place external force is equal to gravitational force. Gravitational force is varying, that means external force acting on it is also varying. So this external force is not constant. Throughout the path. So how to calculate work done by this force? So we have to calculate here work done by a variable force. That's it. Okay. We can use the concept of integration. Suppose the object the object started from this position, and after some time it reaches this position. Suppose this position, let's name it 0 position, s is equal to 0, and here at some s we just take a infinitesimal small displacement. Suppose there is a earth below me having radius 6400 kilometer, and if I am moving this object for a small distance, see, I am moving from here to here, 2 centimeter, 3 centimeter. Observe that gravitational force acting at this place and gravitational force acting at this place is approximately same, because variation in distance from the center of earth is negligible. That's why this quantity is, variation in this quantity force is negligible. So for small displacement we can assume that this force is constant, gravitational force acting on it is constant, and just for counterbalancing we are applying an external force. That's why external force acting on it is also constant. For what? For small displacement. And here I am showing it in zoom position. Suppose this is small displacement. Small displacement ds. Direction is downward. As per definition, we are bringing the object from infinity to that point. And at starting, we assume that we starting from 0 displacement. So put s is equal to 0, and here after some time we take some infinitesimal small element. Now at this position, external force acting on it is constant throughout this infinitesimal path. Okay, this is force acting on it, this is displacement, right? So we can use here the definition of work done, which is f dot ds, right? So small work done by external force in moving this small displacement. This will be equal to f external dot ds. Okay, and this is for small path, and if I am calculating this from infinity to this position, that means from s is equal to 0 to, let's say s is equal to s1, from s is equal to 0 to s is equal to s1. This is work done by, total work done by external force. Now calculate this term. See, direction of I am bringing this object from infinity towards earth. Direction of application of force, external force, is still upward. See, direction of external force is upward. Direction of external force is upward, and the direction of displacement is downward. Angle between them, there is a two vector quantity, angle between them, join tail, see the angle is 180 degree. Now put f ext ds cos 180 degree. It's a definition of dot product from 0 to s1, right? This is magnitude of external force. What is magnitude of external force? Magnitude will be equal to fg. Magnitude of external force will be equal to g mass of earth, mass of object by r square. At this position, what will be? Let's say this position is at a distance r from center. Okay. Cos 180 degree. Cos 180 degree is equal to -1. So now again write it. Work done from 0 to s1, f external ds -1. You can put it negative side outside. That's it. Put the value of external magnitude of external force. What is magnitude? This one, g mass of earth, mass of object by r square ds. See, there are some constant term. This g is universal gravitational constant, mass of earth is constant, mass of object is constant, but r is not a constant. R is varying throughout path, but here we are calculating with respect to s. Our variable is s. That's why limit is with respect to this variable from 0 to s1. But here the variable is r. So first we have to change variable. Either we can change r to s or this s to r. For this, generally we take reference from center of earth or any bigger object, and measuring distance from here is quite reasonable. Infinity point is not defined from where we are measuring this displacement. That's why taking variable r here is more reasonable. Now let's see how to change. There are some kind of relation. Yeah. When we started at this place, suppose this distance is r2 from earth. The distance of starting point is r2. Just for simplification, I put it R2, and after that this R2 will tend to infinity. Okay, just it from infinity to this point, right? R2. Now see, R plus S is equal to R2. This R2 is constant. This is a fixed position. This is fixed position, and this R1 is also fixed position. So this R2 is constant. So here you can write S plus R is equal to R2. This is constant. Now differentiate it. ds plus dr is equal to, differentiation of constant is 0. This will give you ds is equal to minus of dr. Fine. Put it there and take this term outside. Yeah, minus g mass of earth, mass of object, 1 by r square, and minus of dr. At this place we are putting this term. From here, if you take this minus side outside, this will become plus sign. The value is like this. Okay. We are integrating with respect to r. The variable is r. Now we can integrate it. But see, here we were integrating with respect to s, and the limit was of s. S was starting from 0 to this position, s1. Now you have to put limit of r, because integration is with respect to r. Okay. See, this one. When s was 0, 0 plus r is equal to r2. Then r was r2. When s was 0, then r is r2. When s was s1, then r is r2 minus s1. See, r2 is this one minus s1. The remaining portion is nothing but r1. Now it's simple. How you calculate this? Integration of r to the power minus 2 with respect to dr is r to the power minus 2 plus 1 by minus 2 plus 1. This is minus 1 by r. Okay, put it there. G mass of earth, mass of object, minus 1 by r, and the limit is from r2 to r1. Fine. This is equal to G mass of earth, mass of object, minus 1 by r2 plus 1 by, minus 1 by r1 plus 1 by r2. This is work done by external force, and work done by external force is potential energy of the object, and the usual notation for potential energy of object is capital U. This is potential energy of object when you are bringing it from R2 to R1. Now follow the definition. In definition, we are moving object from infinity to R1. It was not from R2 to R1. So infinity to R1. Just put R2 Yeah, when R2 tend to infinity, this implies that 1 by R2 will tend to 1 by infinity, and this will tend to 0. This portion will tend to 0, and the potential energy at R1 will be equal to G mass of earth, mass of object, by R with a negative sign. U is equal to minus of this. Okay, so this is the derived formula to get potential energy at position R1. Now we get the potential energy of object at position R1 and reached our set target. Okay, now see, if anyone say I'm not interested to find potential energy at R1, but I am interested to find potential energy at R3 at this position. So nothing, just change this distance to R3. Okay, so this is generalized formula. I mean, you can put R variable there, and this is generalized formula. Potential energy of any object at any place R situated at outside of this spherical body. The value for potential energy is this. Okay, yeah, there is a shortcut also to calculate this, but this needs some concept from vector. I am showing it just. Yeah, see, if you are moving from R2 to R1, let's rough it first. Yeah, this is R1 and this is R2. Okay, if you are moving an object from R2 to R1, yeah, I am moving this marker from R2 to R1. Direction of displacement is upward, direction of force is, external force is also upward. So you can write work done by external force in moving object from R1 to R2 is integration of small work done at any position R. There is a displacement dr, and work done from moving this infinitesimal object, infinitesimal displacement, is F external dot dr, and we are interested in from R1 to R2. This have an angle 0 degree, so this is nothing but R1 to R2 magnitude of external force into dr, which is equal to R1 R2 G mass of earth, mass of object, by R square dr. What is this? This is work done from R1 to R2. Now observe it. Work done from R1 to R2 is positive, and work done from R2 to R1, force is same, displacement is same, but direction of displacement is different. Direction of force is same in both the case, but direction of displacement is different. In this case, work done is positive because force and displacement have same direction. In this case, work done is negative, but both have same magnitude if final and initial position is fixed. That means in conservative field, no matter what path you followed, the work done by gravitational field is always same between two same point in magnitude. And if you are moving, if work done from R2 to R1 to R2 is this, and but we are interested in work done by external force from R2 to R1. As per definition, we are moving from R2 to R1. This is a negative of work done by external force from R1 to R2. This is valid for conservative field. Okay, and according to definition without changing kinetic energy. Now see, work done by external force from R1 to R2. What is this? This one. So this is R1 to R2 G mass of earth mass by R square dr. And when you calculate, and this will be equal to minus G mass of earth mass object into minus 1 by R R1 to R2. Just put limit there. Minus of G mass of earth mass of object into minus 1 by R2 plus 1 by R1. Again we are moving object from infinity to this point. That means this point will tend to denominator tend to infinity, this term will tend to 0. The value is nothing but G mass of earth mass of object, yeah, with negative sign by R. This is same value. Okay, but you need some more concept from vector to visualize this. Okay, but it's fine. Yeah, so at the time of starting of class we have mentioned that there is a work done what we have studied in class 9. Work done was equal to mgh when there is a height, there is a gain in height of any object. The work done nearby earth surface was mgh. So what was mgh? See it. This is earth. Suppose this is earth, and at the surface any object of mass m is placed. This is initial position, and we raise some height as this is final position. Okay, so initially the object was there this time. So this distance is r1, which is nothing but equal to radius, and this distance is r2. Okay, now see, change in potential energy of object, final potential energy minus initial potential energy. What is final potential energy? Minus of G mass of earth mass of object, this is earth and mass is m, by final means r2. R2 is r plus h, r plus h minus initial means at r. On the surface gravitational potential energy is this. Now after some arrangement we will get G mass of earth, mass of object into 1 by r minus 1 by r plus h. Mass of earth, mass of object into h by r into r plus h. Take this r outside of this bracket and 1 r from here. When you take common from 1 r from here, this term there will be 1 and this is h by r. This is like this. G mass of earth, mass of object into h by r square into 1 plus h by r. See, when this h is much smaller than radius of earth, we are giving a change in height 10 meter, 20 meter, which is very small. Yeah, very smaller than radius of earth. Radius of earth is 6400 kilometer, and in comparison to that, this given height 10 meter or 5 meter is negligible. So for this, h by r will tend to 0. That's for this condition, this term will tend to 0 and the change in potential energy will be equal to this. See, this term is nothing but G, this is M, this term is G, this term is H, mgh. This is positive, that means there is a gain in potential energy. We are raising a object from surface to height. There is a gain. If this h is much smaller than r, then this simplified formula is this mgs. But this is general. Okay. Yeah, I think it's sufficient. We can also find gravitational potential energy inside of this spherical object. Yes, see, one more question was there at the time of definition, that why we are taking spherical object. We have studied object of so many kind. See, we have studied rod, ring, disc. Why we are not taking object like this? Is this object not valid? No. According to definition, every object have its gravitational field. And when you place any another object in the vicinity of gravitational field of this object, it will have some potential energy. But calculation is tough. And for a smaller object, suppose if you are calculating gravitational field between this, okay, then this gravitational force is insignificant in calculus. This is very weak force and generally not significant in the presence of another force, what we will study, like electrostatic force. Okay, so in the gravitational force we study for a bigger object like earth, moon, sun, this kind of thing, and generally these objects have spherical kind of shape. This object have spherical shape. And one more beauty of spherical shape is you can take the whole mass concentrated at center. The gravitational field outside this surface will not change. But for rod, you can't take whole mass at center, and for ring, for disc, you can't take. That's why for